Alright everybody, welcome back as always. Alright, chapter 3 on matter, the last video. Talk about phase and interface. When they're talking about the phases of matter, you go back to elementary school and you were taught that we have gases and we have liquids and solids. But there's actually 8 phases of matter. We only focus on these 3 because these are the 3 that exist on our planet under normal temperatures and normal pressures. But if we get to conditions of high pressure and high temperature, we can strip the atoms of their electrons, creating something called plasma. And we can even go beyond that. We can strip apart the nucleus and start breaking that down under extreme high pressures. But again, we're only talking about the 3 phases of matter that exist on our planet. Now, do understand at any given temperature, although we know from middle school that gas particles tend to move faster than liquid particles, which tend to move faster than solid particles, at least in terms of how they're vibrating, if they're in contact with each other or flowing over top of each other if they're a liquid or a gas, or moving randomly if they're a gas. Not all particles are moving at the same exact speed. So when they come in contact between one phase and another, we can get a spontaneous phase change. In other words, what is evaporation? Well, evaporation is when 2 fast-moving liquid particles hit each other with so much force that when they bounce off, they escape into the gas phase. They're able to do enough work to escape from the rest of the liquid. So we can get spontaneous phase changes without changing the temperature of something. So again, the interface is the boundary between phases. And the phases we're going to focus on are gases, liquids, and solids, which we'll talk about in more detail in chapter 15. All right, so what happens when we have a closed bottle of water? The first example of what we call equilibria. There'll become a point where the amount of spontaneous evaporation is equal to the amount of spontaneous condensation, and therefore we no longer see a change in the material that we're dealing with. Let me show you the notes on that, and I would stop and pause and take those notes. Okay, so take this down. I'll wait until you come back. All right, you're back. All right, so first of all, in order to create a system of dynamic equilibria, we have to have a closed system. So I'm going to use the example of liquid water and water vapor that you would find in a water bottle. So we have 2 things happening here. We have a condition under which in the liquid phase, if 2 particles are moving fast and they hit each other on the surface of the liquid, then they can bounce off and escape into the gas phase. Now remember I said not all particles in the liquid are moving at the same velocity. We said that in average, the gas phase velocity is going to be faster than the liquid phase velocity, but we can still have particles that are moving faster than average. Go back to our Gaussian curve. Okay, so 2 extremely fast moving particles hit each other, and that creates evaporation. And then at the same time, what happens if a slower than average gas particle hits the surface of the liquid? Well, it's going to lose energy, and it may not have enough energy to do the work to bounce off the surface and stay as a gas. Instead, it'll attach to the liquid phase, and that is what we call condensation. So if we keep the lid on the bottle and we leave it together long enough, eventually we'll reach a condition of dynamic equilibria where there's change, there's evaporation and condensation, but you don't see the change because the amount of evaporation equals the amount of condensation. All right. Next part of the video, physical versus chemical properties and changes, and then we'll talk about extensive and intensive properties, and then the 4 signs of a chemical reaction. Now, normally when we're dealing with our course, we're doing labs, so the 4 signs of a reaction should be pretty easy. We said, first of all, in order to have a chemical reaction, you have to create a new material. So I'm not even going to put that on there, that's assumed. But creating that new material may involve a color change. Now again, just because you have a color change doesn't mean you have a chemical change. You have to create a new material. Painting a car red changes the color, but doesn't create a new material. So painting something is not considered a sign of a chemical reaction. Color change, gas evolved. So we pour together two liquids and gases start bubbling, or we put a piece of metal in there and gases start bubbling. Precipitation formed. Pour two liquids together and we get a solid. And then lastly, we have some sort of heat exchange. Now that heat exchange can be endothermic or it can be exothermic. So 4 signs of chemical reaction, pretty easy. All right, we're going to start with extensive and intensive properties. Now, extensive, you can have extensive chemical properties, you can have extensive physical properties, you can have intensive chemical, intensive physical. It's a way of categorizing properties based upon 2 things. Extensive means the property is based upon how much you have. Good example of this is mass. The more copper atoms we have, the more copper mass we have. How much mass depends upon the number of copper atoms. Same thing with the length of a wire. The more copper atoms we have, the longer the wire will be. An intensive property, however, is based upon the identity of the material. For instance, if we look at the density of copper, then we're looking at about, I can't remember off the top of my head, but I think it's about 8.6 grams per milliliter. So let's just call this metal X because I don't want to misquote. But the density of water at room temperature is about 1 gram per milliliter. So those values are based upon the material you have, not how much. Because if you have a glass of water, it'll have a density of approximately 1 gram per milliliter. If you have a bucket of water, it has a density of 1 gram per milliliter. If you have a swimming pool filled with water, it still has a density of 1 gram per milliliter. That density value does not change based upon how much you have. It's based upon the fact that you're dealing with water. All right, so extensive and intensive are 2 ways we can define properties. Now, I always like to ask students, what is a property? Okay, a property is something that describes every particle of a substance. All right, so we can have physical properties where, pardon me, where we are describing the material without involving it becoming a new material. In other words, we can melt something, but when you melt something, you're just taking the solid and turning it into a liquid. You haven't changed the identity of the material. Same thing with boiling, condensation, all of those phase changes. So here's a couple of examples of physical properties. It's malleability, its ability to be hammered into flat sheets, hardness, color, again, luster, shininess, all those properties we talked about with metals and nonmetals and metalloids we could throw in here. They're all physical properties. So what about solubility? Is solubility physical or chemical? Well, solubility just means taking the solute and expanding it and spreading it out into that sphere of hydration. So no, you actually haven't changed the solute. You just spread it out. So therefore, when you're dissolving something, that is a physical, not chemical property. All right, chemical properties, really what you want to look for in the question is look for the words that we've used to describe chemical reactions like combustion, redox, synthesis, decomposition, but there's also some terms that people think you know, even though things have changed. Like, for instance, we don't get a lot of rusting now. Rusting is the oxidation of metals and particularly iron. And, so like I had an iron swing set when I was a little kid, so it had a lot of rust on it, but you have all wooden swing sets now when you're little, so you don't get that sort of rusting effect. So again, rusting would be an orange coating that forms on iron as a result of redox. Tarnishing, same thing. Most people use stainless steel for their eating utensils, but if you have pure silverware, it will tarnish. It will oxidize and get a sort of a grayish white coating on it, and you have to rub a chemical on it in order to get that off and polish up the silver. So I guess your textbook and really any of the test banks that I use all think that students know what tarnishing is, when really you don't experience that. Corrosion is when an acid reacts with a metal and produces a solid, so batteries corrode. And even souring of food. When you change the shape of the proteins that make up the food and denature them, then you're actually changing the composition of food. For instance, milk, when it sours, there's actually a change that goes on chemically. My goodness gracious, that is it. So move on to chapter 3 and 17. For the summer program, again, a lot of people are asking me this question. Look, this chapter 3 on matter and energy involves a lot of stuff. And if you look at the practice tests, I used to do it as one whole test. Over the last 5 years, I've tried to break it up into 2 smaller tests. But over the summer, we're not going to be able to break it up into 2 smaller tests. So 3 and 20 and 3 and 17 are given as one large test. All right? Thank you very much.